All right, today we're diving into a material that really changed the game in dentistry, glass ionomer cements, or GICs for short. Now, these aren't just your run-of-the-mill fillings that plug a hole. Oh no, they're active, almost intelligent materials that completely shifted how dentists think about restorations. So what's the big deal?
Seriously, think about that. What if a filling didn't just sit there, but actually bonded chemically to your tooth? And what if it also released fluoride to help protect against future decay? Well, that's not science fiction. That's exactly what GICs do. It's a material that truly works with your tooth.
So here's what we've got on tap. We're going to start with a little history lesson, a tale of two cements, if you will. Then we'll get into the nitty-gritty of the GIC formula, check out the different ways they're prepared, and see why the mixing process is so crucial. And of course, we'll wrap up with a quick quiz to see what you've picked up.
To really get why GICs were such a breakthrough, you have to look at what came before them. You know, in the world of dental materials, the best innovations often come from taking the best parts of older tech and ditching all the bad stuff.
And that's exactly what happened here. It was a brilliant idea, really. Scientists looked at silicate cements and said, hey, this reactive glass that releases fluoride, that's awesome. Then they looked at polycarboxylic cements and said, and this ability to stick to the tooth, we need that. They basically took the best qualities from both, the fluoride release and the adhesion, and created a whole new material that was stronger, less soluble, and looked a lot better too. A true best of both worlds situation.
So, what's the secret sauce? What's actually inside a glass ionomer cement that makes it work so well? Well, it all boils down to a really specific chemical dance between a powder and a liquid. Let's break it down.
You'll find GICs in a couple of main setups. You've got your traditional powder and liquid systems, sure, but there are also these really clever powder and water systems where the acid component is actually freeze-dried right into the powder itself. But no matter how it's delivered, the core chemistry, the main players, are always the same.
Okay, so the powder is a special kind of glass called aluminosilicate glass. The key word here is ion leachable. Think of it like a tiny molecular salt shaker. When it gets wet, it starts releasing beneficial ions, calcium, aluminum, and the real star of the show, fluoride. That fluoride release is what gives GICs their incredible cavity-fighting power.
The liquid part is an acid, usually polyacrylic acid. Now, the early versions had a major problem. This liquid would thicken up and turn into a useless gel over time. The fix was a fantastic bit of chemistry. By using copolymers instead of homopolymers, they completely stopped the gelling. This wasn't just a small fix, it was a total game changer that gave the material a long shelf life and made it a reliable tool for dentists everywhere.
And then you've got the unsung hero of the formula, tartaric acid. I want you to think of it as the project manager for the chemical reaction. It helps the material start setting quickly, but then it hits the brakes just enough to give the dentist a good amount of time to actually place and shape the filling before it hardens. Without it, the whole process would be a chaotic mess.
And this is how it all clicks together. When you mix the powder and liquid, the acid starts to dissolve the surface of the glass particles. This releases those calcium and aluminum ions. These ions then act like tiny bridges, grabbing onto different polyacid chains and linking them all together. This creates a strong, tangled, cross-linked structure, and that's your final solid cement.
Okay, so we know what GICs are made of. Now, let's talk about how they actually show up in the dental clinic, and get ready for action. There are basically two main ways this goes down.
Over on the left, you see the old-school hand-mixed kit. A bottle of powder, a bottle of liquid, a little scoop. You get the picture. But on the right, that's the modern way. A sleek, pre-proportioned capsule where everything is ready to go. And let me tell you, that capsule has become the standard for a very, very good reason. Now, don't get me wrong. Hand mixing still has its place for some things. But when it comes to restorative fillings, those encapsulated GICs are the absolute gold standard. And it's pretty obvious why.
The benefits are just huge. First off, the manufacturer sets the powder-to-liquid ratio perfectly every single time. That means no more guesswork, no more oops, too much powder. It takes human error right out of the equation. Plus, the mixing is super fast, it's clean, and you can inject the material right into the cavity. It's just incredibly efficient.
You might think, mixing? How complicated can that be? But the truth is, the way you mix a GIC has a massive impact on its final strength. The big enemy we're fighting here is something you can't even see. It's called porosity.
This here is your standard mechanical mixer. Most dental offices have one. You pop the capsule in, and it just shakes it like crazy for about 10 seconds. Simple, right?
It seems effective, but that super fast shaking has a hidden dark side.
Right, here's the problem. For the more fluid types of GIC, that violent shaking is almost like using a whisk to make whipped cream. It whips air into the mixture, creating all these tiny air bubbles and giving it a frothy texture. And every single one of those bubbles is a weak spot in the final filling, which can seriously compromise its strength.
So to fix this, engineers came up with these advanced rotary mixers. Instead of just shaking back and forth, these machines spin the capsule and use centrifugal force. This motion does something brilliant. It shoves the heavier cement to the outside and forces the lighter air bubbles toward the center, effectively squeezing them out of the mix. What you get is a much denser, less porous, and way stronger final material.
Okay, that was a lot to take in. Let's do a quick check-in to see what stuck. I've got a few questions for you. Ready?
And the correct answer is B. Tartaric acid is that traffic controller we talked about. It manages the reaction speed so the dentist has just the right amount of time to work their magic.
Right. For this one, the answer is A. Remember? Copolymers were the breakthrough that stopped the liquid from turning into a useless gel, which was a huge deal for the material's shelf life and reliability.
And for our final question, the answer is C. This is the big one. The single greatest advantage of capsules is that you get a perfect factory set ratio every single time. No guesswork, just predictable, reliable results.
And that brings us to a final thought to chew on. With all these advancements in chemistry and mixing, we can now make these materials with incredible consistency.
Hey there, and welcome. Have you ever really thought about what's happening inside a tooth filling after you've left the dentist chair? We're diving deep into the chemistry of glass Ionomer cements. We're going to find out exactly how a simple powder and liquid can transform into a rock-solid dental restoration. So what's the magic trick here? I mean, how do you go from this simple paste to a material tough enough to handle all the chewing we do? On the surface, yeah, it just looks like mixing stuff. But underneath, chemically, there's this incredible, perfectly timed reaction going on. So let's pull back the curtain and break it all down. Okay, here's our game plan. First, we'll look at the basic chemical reaction itself. Then, we'll meet the key ingredients. After that, we'll walk through the reaction's first stage, see how it gets stronger during maturation, meet the secret ingredient, tartaric acid, that controls everything, and finally, we'll check out the final structure and wrap up with a quick quiz. All right, first things first. At its very heart, this whole setting process is just a classic acid-base reaction. You probably remember this from chemistry class, right? You take an acid, you take a base, you mix them together, and you get something totally new and stable. That simple idea, well, it's the foundation for everything we're about to talk about. It's actually pretty straightforward. The liquid, that's our acid, and the powder, that's our base. When you mix them, they neutralize each other and form a salt. But hold on, we're not talking about the kind of salt you put on your fries. This reaction creates this amazing, complex, cross-linked salt matrix. Think of it like a super strong web or a net that forms, and it cleverly traps the unreacted glass particles right inside of it. Okay, so to really get what's happening, we've got to meet the two main characters in this story. Let's introduce the powder and the liquid. First up, we've got our liquid. This is a polyacid, specifically polyacrylic acid. Now, try to picture a really long chain, like a string of beads. All along that chain, you've got these super reactive parts called carboxylic acid groups. These are basically the chemical hands that are just waiting to grab onto other molecules and build our final structure. This diagram shows it perfectly. See that long backbone of the polymer right here? And hanging off of it, you've got all these COOH groups. These are the action sites. This is where all the magic happens. They're the ones that are going to do all the heavy lifting and link everything together. And our second ingredient is the powder. This is a special kind of basic glass called aluminosilicate glass. Its whole job is to be a source of metal ions. So when our acid liquid attacks the surface of these tiny glass particles, it causes them to release three really important players into the mix: calcium, aluminum, and fluoride ions. So what happens when we mix them? Well, the reaction kicks off immediately, but it happens in stages. The very first stage is all about getting that initial set, that first hardening, and the star of this part of the show is definitely calcium. Okay, so here's what goes down in just the first few minutes. 1, the polyacid goes on the attack, dissolving the outer surface of those glass particles. 2, this causes a huge, rapid release of ions, especially those calcium ions. And 3, These positively charged calcium ions are immediately drawn to the negatively charged acid chains, and they start building bridges or cross-links between them. This is what makes the material go from a liquidy paste to a solid. And this is a really important point. At this stage, the cement has set, but it's not truly strong yet. It's actually still pretty weak and can easily dissolve. In the dental clinic, this is a super critical time window because if it gets contaminated with saliva or water right now, the final filling could be a failure. The initial hardening is done, but the real strength, well, that's still to come. Which brings us perfectly to the second, much slower part of the reaction, which is called maturation. This is where the material really develops its final strength and toughness, and it's all thanks to our other key player, aluminum. This table really breaks down the difference between our two main ions. You've got calcium with its 2+ charge, which is released super fast to get the party started and form that initial set. But then you've got aluminum. It's released much more slowly, and this is the key, it has a 3+ charge. This difference in charge, or valence, is the real secret to the material's final impressive strength. And this diagram shows us exactly why that charge is so important. A calcium ion with its 2+ charge can link two of those acid chains together. But an aluminum ion with its powerful 3+ charge can grab onto 3 acid chains. This creates a much denser, tougher, and more rigid structure. This is the maturation process, and it happens over the next 24 hours, building the cement's real, lasting strength. So why does all this chemistry matter? Here is the single most important clinical takeaway. During this slow maturation phase, the setting cement absolutely must be protected from moisture. If water gets in, it messes with the formation of these crucial aluminum salt bridges, and you end up with a much, much weaker filling. Now, you might be thinking, if the reaction starts right away, how does the dentist have enough time to mix and place it? Great question. The answer is a third vital ingredient that basically acts like an orchestra conductor for this whole reaction: tartaric acid. Tartaric acid is a true master of multitasking. It's incredible. First, it helps kickstart the reaction by getting those ions released faster. But then, it does something really clever. It temporarily holds on to the powerful aluminum ions, telling them to wait. This gives the dentist that critical working time. Then, when the time is right, it lets go of the aluminum and helps guide it into place to form those super strong 3-way links. It's just a beautiful piece of chemical choreography. So, the bottom line is that this clever conductor gives the dentist total control. It gives them enough working time to get the filling placed perfectly, and then, bam, it allows the reaction to finish with a sharp, definite snap set. Okay, let's wrap this up by taking a look at the final structure of our set cement, and then we'll have a quick quiz to see what you've learned. And here it is, the finished product. The final material isn't just one uniform thing. It's actually a composite. You have the unreacted cores of the original glass particles, which act like a filler, and they're embedded within that strong, cross-linked salt matrix we just watched get built. And this matrix also acts as a reservoir for those fluoride ions, which can be released over time to help protect the tooth. All right, time for a little knowledge check. Let's see if you were paying attention. Which ion is the one mainly responsible for that initial set of a glass ionomer cement? Your options are A, aluminum, B, fluoride, C, calcium, or D, tartrate. Which one was the fast actor that kicked the whole thing off? Think back for a second. And the answer is C, calcium. Remember, it's released way faster than aluminum, and it's responsible for making those first crosslinks that give the material that initial set. Nice work if you got that one right. And for our last question, let's bring it all back to the real world. Based on everything we just talked about with that slow maturation phase, what is the #1 clinical reason to protect a setting GIC from moisture? I'll let you think about that one. Understanding the answer to that question is really the key to turning this amazing chemistry into a successful, long-lasting restoration. Let's talk about glass ionomer cements. You know, for some clinicians, they're this incredibly frustrating, really technique-sensitive material. But for others, they're a powerful tool with some pretty unique biological benefits. We're going to dive deep and unpack the clinical challenges and the incredible rewards of really mastering GICs. So here's our game plan. We're going to kick things off with a little showdown against composites. Then we'll get into mastering the critical mixing ratio. After that, we'll learn how to protect the material while it's setting up, unlock the secrets of its amazing chemical bond, and finally, we'll wrap up with a quick check of what you've learned. Let's get right into it. All right, so this brings us to the big question, right? We live in a world of these incredibly strong, super tough composite resins. So why on earth would a clinician ever reach for a glass ionomer? Well, the answer really lies in the trade-offs you have to make. And this table really lays out that choice perfectly. I mean, look, on one side, you've got composites. They're strong, they're tough, they're insoluble. Great, but notice the disadvantages. They don't have any inherent adhesion, and they shrink. Now look at the other side. Glass ionomers give you true chemical adhesion and fluoride release, but the trade-off is that they're more brittle and way more sensitive to water. So it's not about which one is better. It's really about which trade-off you're willing to make for that specific clinical situation in your chair. This leads us right into our first major clinical challenge. See, unlike a composite that just comes ready to go out of the tube, the final properties of a GIC, they're not guaranteed. They depend entirely on you, the clinician, and one very, very specific step. So what do you think it is? What's that one thing that will literally make or break your restoration before it's even placed in the tooth? Yup, it all comes down to the powder-to-liquid ratio. And this isn't just about getting a nice consistency to work with. No, this single factor dictates everything: the final strength, how well it resists dissolving in the mouth, and its ultimate clinical success. If you get this wrong, it's basically a recipe for failure right from the start. And here's where the problem comes in, especially with hand mixing. The optimal mix, the one that gives you the best possible properties, it often feels kind of dry and crumbly. It just doesn't feel right. So what's the natural tendency? You add a little more liquid to get a smoother, wetter consistency. But that tiny bit of extra liquid has a disastrous effect. It absolutely tanks the material's strength and makes it way more soluble. And hey, don't just take my word for it. This is actually codified in international standards. Take a look at the second row in this table. For a restorative GIC, it requires a minimum compressive strength of 130 megapascals. If your powder-to-liquid ratio is off, you simply will not hit that number. Your restoration is compromised before you even place it. So how do we solve this? Well, the modern solution is actually brilliant in its simplicity: encapsulation. The manufacturer pre-measures the powder and liquid perfectly into a little capsule. You just pop it in a mechanical mixer for a few seconds, and boom, you get a perfect, consistent mix every single time. It takes all the human error right out of the equation. Okay, so let's say you've nailed the mix. It's perfect. Well, the next challenge begins the instant you place that restoration. The GIC setting reaction is a long, drawn-out process, and it's incredibly vulnerable in its early stages. And this right here is the critical window. For about the first hour after you place it, the material is just so vulnerable. Any moisture contamination, we're talking even just a little bit of saliva, will permanently weaken the material and make it more soluble. And the damage is totally irreversible. So, what do? We have to create a temporary shield. It's a simple protocol. As you can see in these steps, once the cement reaches its initial set, you immediately, and I mean immediately, apply a coating. A simple varnish can give you some short-term protection, but honestly, for a really durable long-term shield, a resin bonding agent is the best way to go. This step is absolutely non-negotiable for success. Okay, we figured out the challenges of mixing and setting. Now, let's turn to the ultimate reward for being so careful: glass ionomer's unique ability to form a true chemical bond with the tooth itself. This is where the magic happens. I mean, this is the really cool part about the material. It's not just some mechanical lock and key situation. So how does it actually work? Well, the science is fascinating, and there are a couple of leading theories. The first theory is called chelation, which is basically a powerful molecular handshake. As you can see in this diagram, the long polyacid chains in the GIC are like little arms, and they reach out to chemically grab, or chelate, the calcium ions on the tooth surface. It's a direct, really powerful bond between your restoration and the tooth. Now, the second major theory is all about reprecipitation. Here's how it works. The acid from the cement initially dissolves the very top layer of the tooth. Then, as the cement starts to set and the pH begins to rise, a new, complex hybrid layer, made of material from both the tooth and the cement, precipitates back onto the surface, effectively fusing the two together into one. And it gets even cooler when we talk about dentine, because there might be an extra link in that chain. Beyond just bonding to the minerals, Some researchers believe the carboxylic acid groups in the GIC could also be forming hydrogen bonds or metallic ion bridges directly with the collagen inside the dentine. That would create an even more integrated, powerful bond. Okay, we have covered a lot of ground, from the nitty-gritty of mixing all the way to the chemistry of bonding. Now, let's see what's stuck with a quick knowledge check. First question, adding more liquid to a GIC mix will? What do you think? If you said C, weaken the final restoration, you are absolutely right. Remember, it also makes it more soluble. It's the most common mistake and the one that leads straight to clinical failure. All right, next up. Why must a freshly placed GIC restoration be varnished? The answer is B. It's all about protecting it from moisture contamination. That varnish is the shield it needs during that critical initial setting phase. And for our final question, what's the primary theory for how GIC chemically bonds to tooth enamel? It's D. It's all about that molecular handshake we talked about, the process of chelation with calcium ions on the tooth surface. If you take away only one single thing from this entire explainer, let it be this direct quote from the source material. The properties of glass ionomers are critically dependent upon the powder/liquid ratio. Seriously, everything else, strength, solubility, success, it all flows from getting that one step right. So that really brings everything together. Glass ionomers, they demand a ton of respect for their technique sensitivity, but in return, they offer these incredible rewards in chemical adhesion and biocompatibility. So the question I want to leave you with is this. Now that you know these specific challenges and these incredible strengths, in which clinical situations would you now choose a glass ionomer over a composite? We're diving into a dental material that's so much more than just a simple filling. We are talking about glass ionomer cements, a material that can actually bond to teeth, protect them, and, get this, even behave in a smart way. We're going to explore the science behind how they work, why they sometimes fail, and what that whole smart thing really means. So here's how we're going to break it down. First, we'll look at the tricky business of getting them to stick. Then we'll ask if they're actually safe for the living part of the tooth. After that, we'll uncover their secret thermal properties, which is super cool. And finally, we'll wrap it all up with a quick quiz to make sure it all sinks in. All right, let's jump right in. So first things first, how in the world do we get these cements to stick so well to a tooth? Well, the answer isn't as simple as just using a really strong glue. It all starts with understanding the surface we're trying to bond to in the first place. When a dentist drills a tooth to clear out a cavity, the surface that's left behind isn't perfectly smooth or clean. Nope, it's actually covered in this microscopic layer of debris from all that drilling. And that layer, that's the very first hurdle we have to get over. This stuff is called the smear layer. The best way to think of it is like trying to stick a poster to a dusty wall. If you don't do something about that dust, the poster isn't really sticking to the wall, is it? It's just sticking to the dust. So the question becomes, how do we clean up this microscopic dust without messing up the wall underneath? Now, how you clean that surface is absolutely crucial. If you use something too aggressive, like citric acid, it's kind of like using heavy-duty sandpaper when you just needed a damp cloth. Sure, it gets rid of the smear layer, but it also damages the dentine itself by stripping away the calcium. And here's the kicker. The glass ionomer needs that calcium to create its chemical bond. So the harsh acid literally removes the very thing the glue needs to grab onto. The much better approach is using a gentler conditioner like polyacrylic acid. It just modifies the surface enough, leaving the calcium right where it needs to be, ready for a good, solid bond. But here's a little twist. Even with the absolute perfect surface prep, the bond strength is only about 1 to 3 megapascals. Now, a megapascal is just a unit for measuring pressure, but for dental materials, that number seems kind of low, right? And, well, it is. It's surprisingly weak, which makes you wonder, why are we even using this stuff? And this is the real secret. The problem isn't the bond. The problem is the GIC material itself. The material's own internal strength is actually lower than its bond strength. So when you put pressure on it, the bond to the tooth holds on tight, but the cement itself cracks and breaks from within. This is called cohesive failure. Think back to that sticker analogy. The glue on the sticker is great, but the paper of the sticker is weak, so it just tears in half. That's what's happening here. And wow, this chart just lays it all out, doesn't it? When you put GICs side by side with modern resins, which can get up to 16, even 20 megapascals, you really see that huge gap. This is exactly why understanding this cohesive weakness is so critical for a dentist. It tells them that GICs are great for low-stress areas, but probably not the best choice for rebuilding a major chewing surface that takes a real beating. Okay, let's switch gears a bit. Now, given that GICs are fundamentally based on an acid-base reaction, that begs a pretty important question, right? Is this stuff actually safe to put inside a living tooth, right next to the sensitive pulp? So how can an acidic cement possibly be safe? Well, it's pretty genius, actually. And it comes down to two main things. First, the polyacrylic acid isn't super aggressive to begin with. But the real magic is the size of the acid molecules. They are enormous, tangled up chains. Seriously, picture a big clump of spaghetti. They're simply too big and clumsy to wiggle their way down the tiny little tunnels in the dentine to reach and irritate the pulp. They basically get stuck, especially once they start latching onto the calcium in the tooth. Okay, so that makes sense. But it leads to the next logical question. Are we always good to go no matter what? What happens when a cavity is so deep that you've only got a paper-thin layer of dentine left, protecting that delicate pulp? And yeah, for those really deep cavities, you do take an extra step. The standard way to handle it is to use a calcium hydroxide liner, which is like a little protective shield. But the key word here is selectively. You only put it on that tiny little spot right over the pulp. You definitely don't want to slather it over all the exposed dentine because that would totally cancel out the GIC's amazing ability to chemically bond to the tooth. And, safety isn't just about the acid. It's also about the purity of the ingredients. The glass powder in the cement comes from raw materials that might have tiny, tiny traces of heavy metals. Because of this, international standards are incredibly strict. They limit things like arsenic and lead to just a few parts per million, which ensures the final product is extremely safe to have in your body. All right, now for what I think is one of the coolest properties of GICs. How do they protect the tooth from the daily shock of, say, hot coffee or cold ice cream? The answer reveals a surprisingly clever design. First off, GICs are fantastic insulators. The key property here is something called thermal diffusivity, which is really just a fancy way of saying how quickly heat moves through something. Think about it like this. If you have a metal spoon and a wooden spoon in hot water, the metal one gets hot super fast, right? The GIC is like the wooden spoon. It has a very low thermal diffusivity, almost identical to natural dentine, and that means it shields the pulp from the shock of those sudden temperature changes. Even the heat that's created as the cement hardens, that's an exothermic or heat-releasing reaction, it's super minimal. We're talking a temperature rise of only about 2 to 5 degrees Celsius for a normal-sized filling. That's well within the safe zone, so no worries about it harming the pulp. But hold on, that's just insulation. What about the bigger problem? Most materials expand when they get hot and shrink when they get cold. Just imagine that happening in your tooth every single day. With every sip of coffee, every bite of ice cream, that constant movement should, in theory, break the bond over time and cause the filling to fail. But GICs have this amazing trick up their sleeve. This is its smart behavior. It's so clever. You see, the set cement isn't totally dry. It has water molecules locked into its structure, and it uses this water to perfectly balance out temperature changes. So when you drink hot coffee, the GIC starts to expand, but at the same time, it pushes a tiny bit of water out, which perfectly cancels out that expansion. Then when you eat ice cream, it starts to shrink, but it pulls a tiny bit of water in from the mouth, canceling out the shrinkage. It's this incredible self-regulating system that keeps it perfectly stable and protects that precious bond to the tooth. Okay, we have covered a ton of ground there. Let's do a quick knowledge check to make sure the most critical points really landed. First one up. Remember when we were talking about prepping the tooth surface? We talked about a harsh approach versus a much gentler one. Which one was the winner for GICs? Yep, the correct answer is C, polyacrylic acid. The gentle conditioning is the way to go because it prepares the surface without stripping away that essential calcium that you need for the chemical bond. Next question. When a GIC filling breaks, what's usually the root cause? Is it the bond to the tooth that gives way, or is it something else? You got it, it's B. The cement itself actually breaks before the bond does. The material's own internal strength is the true limiting factor. Remembering this concept of cohesive failure is absolutely key to understanding where and when this material can be used successfully. And that brings us to the end. The story of glass ionomer cement is about more than just teeth. It's a fantastic early example of a smart material, one that doesn't just sit there passively, but actively interacts with its environment to do its job better. It really makes you wonder, doesn't it? What other problems in medicine could we solve with materials that can basically think for themselves?
Let's talk about a dental material that is a complete paradox. Seriously. On one hand, it's smart. It can actually protect a tooth from future decay. But on the other hand, it's so brittle it can literally shatter. We're diving into glass ionomer cements, or GICs, and in this explainer, we're going to unpack both sides of this really fascinating story.
So just think about this for a second. What if a filling did more than just, fill a hole? What if it could act like a tiny, built-in bodyguard for your tooth, actively fighting off future problems? Well, that's pretty much the core promise of GICs.
So this smart part of the GIC, what is it? Well, it's basically a chemical superpower. It has this unique built-in defense system that goes to war against new cavities right where they're most likely to pop up. And the secret to the superpower? It's these guys right here, mobile fluoride ions. Now, inside the set GIC, you've got these fluoride ions that aren't chemically locked down. You can think of them as tiny little free agents, just waiting to be sent out on a mission.
Okay, so how does this actually work? It's a really cool, simple process. These little fluoride ions, they just diffuse out of the cement and seep right into the tooth. Once they're there, they kick out the weaker parts of the tooth's enamel and replace them, making the whole structure fundamentally stronger and way more resistant to acid attacks from bacteria. And that's the key takeaway. The filling itself is actively protecting the tooth around it.
This quote just sums it up perfectly. This isn't some one-and-done deal. The GIC is basically giving that tooth a continuous low-dose fluoride treatment for the entire life of the filling. Pretty amazing, right?
But wait, the story gets even smarter. This whole system doesn't just run out of juice over time. Nope, it's way more like having a rechargeable battery for your tooth.
So here's the cycle. It's got 3 stages. First up, release. The GIC lets out that fluoride to protect the tooth. Then, protect. Those ions get to work, strengthening the enamel. And then, this is the really cool part, recharge. The cement actually soaks up new fluoride from outside sources, topping up its little reservoir so it can do it all over again.
So you might be asking, where does it get this new fluoride? Well, it gets it from your everyday routine. We're talking fluoridated toothpaste, mouthwashes, even the water you drink. They all help top up this protective little tank. Your filling literally becomes an active partner in your dental health.
Okay, we have definitely covered the smart, but now it's time to face the music and talk about the brittle. Because for all its chemical cleverness, GIC has a major physical weakness that you just can't ignore, and that is its fragility.
This chart, wow, it tells the whole story in one quick look. When you look at flexural strength, and that's its ability to resist bending forces, GICs are just so much weaker than modern composite resins. We're talking about 20 megapascals compared to over 70. That is a huge difference.
This weakness creates what you could call clinical no-fly zones. You would absolutely never use a GIC to fix the corner of a front tooth that takes all that biting force, and you wouldn't use it in any other high-stress area on a permanent tooth where it's probably just going to crack under pressure. It's just not what it's built for. But, and this is a big but, here's where it all gets a little confusing. If you only looked at the official standards, you might get a totally different idea about GIC's strength. So let's dig into why that number can be so misleading. Okay, check this out. This is the official ISO standard. It says a restorative GIC needs a minimum compressive strength of 130 megapascals. Now that sounds pretty darn strong, doesn't it? Especially when you remember that 20 megapascals flexural strength we just saw.
And that brings us to the million-dollar question. How can something be so strong and so brittle at the same time? Well, think about a ceramic floor tile. You can stand on it all day long. That's high compressive strength. But if you try to bend it, even just a little, what happens? It snaps. That's low flexural strength. GICs behave in almost the exact same way.
And this slide spells it out plain and simple. Compressive strength is all about resisting being squeezed, and GICs are great at that. But flexural strength is about resisting bending or pulling, and that's where they really struggle. The problem is the ISO standard only measures compression, which just doesn't tell you the whole story of how it's going to perform in your mouth.
Now, not all GICs are made the same. Their strength really depends on the mix. For a tough restorative cement, you're looking at a powder-to-liquid ratio of about 3:1 by weight.
Now compare that to a GIC you'd use for luting, cementing a crown. That ratio is way lower, more like 1.5 to 1. It makes for a much runnier mix, and as a result, a much weaker material. This just goes to show how critical it is to get that manufacturer's ratio exactly right.
So, we know the powder-to-liquid ratio is huge, but there's one last critical factor that decides the final strength of a GIC restoration. Let's talk about the true enemy of GIC strength. And that enemy is one word: porosity. We're talking about tiny little air bubbles that get trapped when you're mixing it. Every single one of those bubbles is a weak spot, the place where a crack can start. That's why careful hand mixing is absolutely essential to keep those bubbles out and get the maximum strength.
Phew! We have covered a lot of ground. So now let's do a little quick-fire quiz to see what you've learned about the two-faced nature of GICs. Ready?
First question. The rechargeable nature of GIC lets it soak up fluoride from. The answer is A. Toothpaste and mouthwash. Yep, the cement actively pulls in fluoride from these everyday sources to refill its protective reservoir.
Question number 2. Why can the official ISO standard be misleading when it comes to GIC's strength? The answer is B, compressive strength. The standard only tells you how good it is at being squeezed, but it totally ignores its big weakness, which is bending or flexural strength. And for our final question, besides the powder-liquid ratio, what's the big enemy of strength you have to control during mixing? The answer is C, porosity. Every single trapped air bubble is a ticking time bomb for a fracture, so that careful mixing technique is just crucial. So we end right back where we started, looking at the two sides of this incredible material. GICs offer a unique therapeutic benefit that literally no other material does. And that leaves us with one last thought. As dental materials keep getting better and better, will we finally find a way to overcome its fragility and let the undeniable intelligence of GICs truly shine? All right, let's talk about glass ionomer cements, or GICs. Now, these materials are a huge deal in dentistry, but honestly, they're a bit of a puzzle. They're designed to be strong, yet they can wear down. They're made to look like a tooth, but not always convincingly. And the weirdest part? Sometimes they can completely vanish on an X-ray. We're going to unpack these 4 critical challenges to really understand when and why a dentist reaches for this fascinating and kind of tricky material. So here's our game plan. We'll kick things off with the challenge of simple wear and tear. Then, we'll see how these GICs hold up against an acid attack. After that, we'll get into the tricky question of aesthetics, and then tackle what I call the invisibility problem. And, of course, at the end, we'll have a quick quiz to make sure it all stuck.
Okay, first up, the challenge of wear. We're talking about how this material handles the constant daily grind of chewing, brushing, you name it. So let's find out what actually happens to its surface over time.
To really get this, I want you to picture an old cobblestone street. You've got these really hard stones, right? And they're all held together by a much softer mortar. Now, over years of traffic and rain, what happens? The soft mortar erodes away first, leaving those hard cobblestones sticking out. Well, a glass ionomer filling behaves in almost the exact same way.
Now, this property has a technical name, abrasion resistance, and frankly, this is a known weak spot for glass ionomers. Their resistance is pretty poor, which leads to that rough cobblestone surface we just talked about and a gradual loss of the filling's original shape. So what's actually causing this roughening? It really boils down to 2 things. First, you've got general wear. That's the softer matrix, our mortar, just eroding away and exposing the hard glass particles, our cobblestones. But here's the really ironic part. Even the act of polishing the filling can make it rougher by stripping away that soft matrix and leaving those hard glass cores poking out. Okay, so we've moved from physical wear and tear to a full-on chemical assault. This brings us to our second big challenge. How in the world did GICs handle acid? So picture this scenario. A patient gets a brand new GIC filling, they leave the office, and maybe an hour later they decide to have a nice big glass of orange juice. What happens in that moment is absolutely critical for the long-term survival of that restoration. What's happening here is called acid erosion. And this isn't really a flaw in the material, it's just a part of its fundamental DNA. Glass ionomers are essentially salts created from an acid-base reaction, and because of that, they're just naturally vulnerable to being broken down by other acids. And this is exactly where our first 2 challenges team up. Right after it's placed, a filling is at its most vulnerable. So when acid from your food or drink hits it, the surface immediately starts to soften. And what happens to a soft surface? It gets worn away by physical forces way more easily. It's a devastating 1-2 punch. Chemical weakening followed by rapid mechanical breakdown. Now, this problem is so significant that it's actually regulated by an international standard. The rule sets a very, very specific limit. A GIC filling is not allowed to lose more than 0.05 millimeters of its surface per hour when it's exposed to acid. That's a tiny number, which shows you how serious this is.
And here it is, the official requirement straight from the ISO 9917 standard. You can see it right there. For every type of GIC, whether it's for a filling, cementing a crown, or just acting as a protective base, the maximum erosion is that 0.05 millimeters per hour. And they measure this with something called a jet test, where they literally blast the cement with lactic acid to see how much of it disappears. So how can dentists actually fight back against this? Well, they're definitely not helpless. They can coat the new filling with a protective varnish while it's setting. They can choose to use a faster setting material. And maybe most importantly, they have to be incredibly precise about mixing it at the correct powder-to-liquid ratio. All these steps help create a much more resilient filling. Okay, we've covered strength and durability. Now for challenge number 3, aesthetics. How well can a GIC pull off a chameleon act and just blend in with a natural tooth?
Aesthetically, glass iometers are, well, they're okay. They can give you a pretty reasonable match, especially to the dentin part of the tooth. Their translucency actually comes from those leftover unreacted glass cores we talked about, which lets some light pass through. But let's be real, when you put them side by side with resin composites, GICs almost always come in second place. Resins are just more polishable and come in a much bigger range of shades.
And this creates a massive headache for the manufacturers, and this quote sums it up perfectly. If they try to tweak the glass chemistry to make the material stronger or react better, they often end up making it more opaque and chalky looking, which just kills the aesthetics. It is a constant, frustrating trade-off.
Okay, this brings us to our final, and maybe our strangest challenge yet. It's not about how the filling looks in the mirror, but how it appears on an X-ray. This is what I call the invisibility problem.
Think of it this way. A filling that doesn't show up on an X-ray is basically a ghost. The dentist knows it's there, but they have absolutely no idea what's happening underneath it. Is there new decay starting to creep in? It is literally impossible to know without drilling out the entire filling just to take a look.
The technical term for this is radio opacity. It's just the ability of a material to block X-rays so it shows up as white or light gray on the film. And the thing is, conventional GICs just don't have this property. They're made of elements with low atomic numbers, which means they just don't have enough density to stop an X-ray beam in its tracks. So how do they fix this? Well, they add heavy metals into the mix, like barium. But, and this is a huge but, it creates another one of those major trade-offs we've been talking about. As soon as you make the GIC visible on an X-ray, you cause a significant loss of its translucency. So the fix for the invisibility problem ends up hurting the aesthetics. You just can't win.
Okay, wow. We have covered a lot of ground. Wear, acid, aesthetics, and radial opacity. So it's time for a quick quiz to see what you've learned. You ready?
First question for you, what is the primary reason that the surface of a GIC gets rough over time? Is it A, chemical erosion from acids, B, the softer matrix wearing away, C, just poor polishing technique, or D, expansion because it's absorbing water?
And the answer is B. The softer matrix wears away. It's that core mechanism, just like the mortar washing away from between the cobblestones, leaving those hard glass cores sticking out.
All right, question number 2. Why are conventional GICs like ghosts on a dental X-ray? Is it A, because they're too dense, B, because they're made of plastic, C, because they contain metallic ions with low atomic numbers, or D, because they aren't fully set?
The correct answer is C. They contain metallic ions with low atomic numbers. These elements just aren't dense enough to stop X-rays, so the filling looks dark on the film, making it really hard to distinguish from decay.
And this really brings us to our final thought. As we've seen, GICs are just full of these compromises. You're constantly trading aesthetics for strength or visibility on an X-ray for translucency. So the real question for a clinician is this. Given all these challenges, in what situation would a GIC's unique benefits, like its amazing ability to release fluoride, actually outweigh all of these compromises? Answering that, well, that's the art and science of modern dentistry. So, have you ever wondered what would happen if you tried to make a tooth filling out of, well, both metal and glass? Sounds kind of weird, right? But it was a real thing in dentistry. We're going to dive into the story of cements. It's this fascinating hybrid material that was supposed to be a total game changer. But, well, it ended up teaching us a really important lesson instead. So, This was the big question that scientists were wrestling with, you know? What actually happens when you take a glass-based filling and you try to beef it up with tiny metal particles? The dream was, of course, to get the best of both worlds. You'd get the amazing bonding power of glass, but with the raw strength and toughness of metal. And that question, right there, is really the heart of the whole Cement story. Okay, so to really get why scientists were so excited about this metal and glass idea, we have to back up a little. We need to talk about the material they were trying to improve in the first place, which was glass ionomer cement. Now, this stuff was revolutionary for sure, but it had this one major, glaring weakness.
So, glass ionomer cements, or GICs for short, had two amazing things going for them. One, they could actually chemically bond right to your tooth structure. And two, they released fluoride, which is awesome for fighting off future cavities. But, and this is a big but, they just weren't very strong. They were brittle and they wore down really easily, especially from all the grinding and chewing. So, for a filling on a back molar that takes a lot of punishment, yeah, GICs were pretty much a no-go.
And that weakness, that brittleness, and the fact that they wore out so fast is exactly what pushed researchers to think outside the box. They thought, okay, if the glass by itself isn't tough enough, what if we could strengthen it from the inside? And that's how we got to the Cement, this really cool hybrid idea.
So what is a Cement exactly? Well, the name pretty much tells you everything you need to know. It's a mashup of CER, ceramic, and metal. At its core, it's just a glass ionomer cement, which is a type of ceramic, but it's been beefed up with metal particles. The idea was super simple, right? Keep all the good stuff from the GIC, but use the metal to fix the weak parts.
And the concept here is actually brilliant in its simplicity. The best way to think about it is like reinforced concrete. You know how concrete is super strong when you compress it, but it can crack if you pull on it? That's why we put steel rebar inside. It makes the whole thing way tougher. Well, a Cement is the exact same idea, just on a microscopic scale. The glass cement is your concrete, and the little tiny silver particles are the rebar. They're in there to stop cracks from forming and to fight off wear and tear. Okay, so great idea, right? But how in the world do you actually make this stuff? I mean, how do you get metal and glass to become one single powder that a dentist can use? It's definitely not as simple as just, stirring them together in a bowl. Let's walk through how it's done.
The whole process is actually pretty high-tech. First, they take super fine powders of both glass and silver and mix them up. Then they take that mix and press it under a ton of pressure to form these little pellets. Now this next part is the real magic. They heat those pellets up in a furnace to about 800 degrees Celsius. That's hot. And what that does is it actually fuses the silver particles right onto the surface of the glass particles. They become chemically bonded. And then finally, they take these new fused pellets and grind them all the way back down into that fine powder that's ready to be used as a fill.
So you've got a solid theory, and a really clever way to make it. The hope was that this new metal-infused cement was going to be it, the ultimate material for fillings. But as we see all the time in science, a beautiful idea on paper doesn't always work out in the real world. So the big question is, how did Cements actually do when they were put to the test?
Yeah, this is really the make-or-break question, isn't it? Did that microscopic silver rebar do its job? Did it actually make the fillings tougher and more wear-resistant? Did it solve that fundamental problem that the original glass ionomers had?
Well, the results were surprising and honestly kind of disappointing. Remember the two big goals: improve wear resistance and improve flexural strength. That's basically how much it can bend before it snaps. And in those two key areas, Cements were no better than the originals. A total letdown. Now, they did get a little better in some ways. They had higher compressive strength, so they could handle being pushed on, and a better fatigue limit, meaning they held up to repeated stress a bit better. But failing on the main goals of wear and tear, that was a huge blow.
And on top of that, there was a really obvious problem you could see just by looking at it: the aesthetics. Regular GICs are tooth-colored, so they look natural. But the second you add silver into the mix, bam, you get this dull, gray, metallic-looking filling. So right away, Cements were completely out of the question for any tooth that people could actually see.
So, making these changes also led to some other things they weren't really expecting. There was some good news. Because they didn't have to worry about the color anymore, they could use a different kind of glass that was more reactive. So ceramics actually set a lot faster. Plus, the silver in them makes them show up super clearly on an X-ray, which is a huge help for dentists. But then there was the bad news. Since you're replacing some of that fluoride-releasing glass with metal, which doesn't do anything, well, Cements released a lot less fluoride. And that kind of defeats one of the big advantages of using a GIC in the first place. Okay, so let's zoom out and look at the whole picture. We have this material that started as a brilliant idea, but in practice, its performance was mixed. It looked pretty bad, and it had these weird side effects. So where does that leave Cermets? What's the final verdict on their place in the history of dental materials?
This quote from the actual research really nails it. It says the hope was that the metal would have a significant effect on brittleness and abrasion. You can really hear the optimism there, right? This was supposed to be the solution to a problem everyone knew about.
All right, so here's the bottom line. Cermets were an incredibly clever idea, no doubt about it, but the real-world results just didn't live up to the theory. They didn't fix the main problems, wear and brittleness, and at the same time, they looked bad and released less fluoride. So in the end, you could say their biggest contribution wasn't really as a great filling material, it was the valuable lesson they taught us about material science. Just because you add something strong to a mix doesn't automatically make the whole thing stronger. The chemistry is always way more complicated than that.
Okay, that was a deep dive. So let's do a quick knowledge check to see what you took away from all that. I've got a few questions for you. First one up, what was the primary weakness of Cermets that really limited their use in the visible parts of the mouth? Was it A, B, C, or D? I'll give you a second. Yep, the answer is B, that gray metallic color. Adding silver made them just impossible to blend in. All right, next question. We know Cermets did improve some things. So compared to regular GICs, which of these properties saw a significant improvement? The answer here is B, compressive strength. Remember, they didn't get better at resisting wear or bending, but they did get better at handling direct chewing forces. Okay, last quiz question, a bit more of a thinker. What's the main reason Cermets release less fluoride than the conventional GICs? The key here is just simple substitution, really. The metal particles don't do anything. They're inert. They don't have any fluoride to release. And since they take up space in the filling, there's just less room for the glass that does release the fluoride. Less glass, less fluoride. Simple as that.
And that really brings us to our final takeaway. The whole story of the Cermet is a perfect example of how science works. Adding metal wasn't the magic fix everyone hoped for, so it makes you think, right? If that didn't work, what's next? What other kinds of materials, what new chemistries are scientists looking into now to try and create that perfect ideal tooth filling? The search is always on, and that's what's so cool about scientific progress. Every failure or dead end is really just a lesson that points you in a new direction.
We're jumping into a material that's a real workhorse in dentistry, glass ionomer cements. We're going to skip the deep chemistry and get right into clinical mastery, the how, and maybe more importantly, the why you'll use GICs to solve those everyday problems you see in the clinic. Let's get right to it. So, let's kick things off with a question about a common clinical headache: fillings right at the gum line. Why are these cervical restorations such a pain to place, and why do these seem to fail so often? This is the core problem that glass ionomers are basically built to solve. And by the time we're done here, you'll see exactly why they're the go-to material for this. Okay, here's our game plan. We'll start with the main mission for GICs, tackling problems at the root level. Then, we'll get into the absolute must-know rules for preparing the tooth. After that, we'll look at some other cool uses, check out a modern, super conservative technique, master the tricky art of moisture control, and finally, unlock the secret to GIC's famous chemical bond. So, what is it that makes GICs the perfect solution for those tricky gumline cavities? Well, it really comes down to two killer features. They chemically bond directly to the tooth, and they release fluoride. That 1-2 punch makes them the ideal material for restoring tooth loss right at the root, which is exactly where our patients need the help. Now, let's break down the two main culprits we find in this area. On one hand, you've got root caries, pretty much classic decay on a soft, vulnerable surface. On the other hand, you have cervical abrasion, which is a much more complicated mix of mechanics and chemistry. Understanding how they look and what causes them is totally fundamental to getting the treatment right. Let's zoom in on root caries for a second. The dentin on the root is way softer than enamel, right? So decay doesn't just drill down deep. Instead, it spreads out sideways, kind of like pancake batter in a pan. So what happens? When you clean out all the decay, you're left with a cavity that's typically really broad and pretty shallow. Remember that shape. It's going to be important in a bit. And here's the other type, the cervical abrasion lesion. For years, we just blamed this on people brushing their teeth too hard. But the modern take is way more sophisticated. We now know it's a perfect storm of three things: acidic diets, brushing habits, and, this is the big one, the tiny flexing of the tooth when you chew. This whole process creates a hard, super polished, decay-free surface. And that glossy, burnished dentin, it's a total nightmare to bond to. But don't worry, we've got a fix for that coming right up. Okay, so we figured out what the lesion is. Now let's talk about prepping the tooth. You can have the best material on the planet, but if you don't build a solid foundation, that restoration is just doomed to fail. And for GICs, this means you got to follow some very specific rules. This is rule number 1, and it's non-negotiable. You absolutely cannot have thin, feathered, knife-edged margins. Why? Simple. Glass ionomer is a brittle material. Just think about a ceramic plate. The middle is strong, but that thin edge will chip if you even look at it wrong. A thin GIC margin will do the exact same thing. It'll fracture, create a gap, and the whole restoration will eventually fail. So, if a knife edge is a no-go, what's the answer? It's the butt joint margin. And honestly, the woodworking analogy here is perfect. If you want to glue 2 pieces of wood together for maximum strength, you butt them up flat against each other, a clean 90-degree angle. You don't shave one down to a point. We need that same strong 90-degree shoulder in the tooth for the GIC to sit on so it can resist breaking. And here it is, the magic number you need to burn into your brain, 0.75 millimeters. That butt joint margin has to be at least 0.75 millimeters deep. This isn't just a suggestion, it's a structural requirement. It gives the material enough bulk to handle all the stress. Anything less, and you're just asking for that chipping we just talked about.
All right, time for a quick pop quiz. What was that absolute minimum depth we need for our butt joint margin? The answer is C, 0.75 millimeters. Lock that number in your head. It's one of the most important things for clinical success with GICs.
Now, while GICs are the undisputed champs for cervical lesions, their special properties actually make them useful for a lot of other things too. So let's explore a couple of other key places where they really shine. The 2 other big applications we're going to touch on are for fillings between the front teeth, those are class 3 cavities, and as a fantaft filling material in kids for their deciduous or baby teeth. You know, back in the day, using GICs on front teeth was, well, it was a non-starter. The first versions were really chalky and opaque, and they just didn't blend in at all. But wow, material science has come a long way. The GICs we have today have much, much better translucency and aesthetics, making them a totally reasonable choice for class 3s, especially if the patient is at high risk for cavities. When it comes to pediatric dentistry, GICs are a real game changer. Because they chemically bond, we can be way more conservative when we prep the cavity. We don't need to drill away extra tooth just for retention. And less drilling? I mean, that's a huge win for any kid in the chair. Plus, while a GIC might not last 30 years in an adult molar, it's definitely durable enough to last for the life of a baby tooth. Okay, now let's look at a really elegant, advanced technique that makes the most of GIC's properties to save as much healthy tooth as possible. This is the tunnel preparation. So instead of the old school way of cutting a big box from the chewing surface all the way down to the decay, the tunnel prep is super minimally invasive. The dentist creates a tiny little access tunnel, maybe from the top or the side of the tooth, that leads right to the decay. Then they clean out the cavity through that tiny path and inject a flowable GIC to fill it all up from the inside. So what's the big deal? Why is this so great? It all comes down to preserving the marginal ridge. That little ridge of enamel isn't just a bump, it's a critical piece of the tooth structure, kind of like a crossbeam in a building. It holds the whole tooth together. By leaving it intact, the tunnel prep keeps the tooth incredibly strong and drastically lowers the risk of it fracturing down the road. Okay, we've prepped the tooth, we've picked our technique. Now we get to something that's super important but often misunderstood when using GICs, managing moisture. This material is incredibly picky about its environment. This is absolutely crucial. The way glass ionomer sets is a long chemical reaction that needs water to work properly. So right after you place it, the surface is really vulnerable. If it dries out too fast, it'll get these little surface cracks. But if it gets swamped with saliva, the top layer won't form right and it'll just wash away. You're basically walking this tightrope trying to keep the surface perfectly hydrated while it sets. And that brings us to our last and maybe the most important section. How do we actually get the GIC to stick? That chemical bond is its superpower. But you, the clinician, have to prepare the surface just right to actually unlock it. There are 2 main villains that will completely prevent the chemical bond from happening. The first is that burnished or eburnated dentin we saw in those abrasion cavities. And the second is any tooth surface that's been contaminated with saliva. Saliva immediately lays down a film that acts like a total bond breaker.
Let's go back to that hibernated dentin. Basically, it's the tooth's defense mechanism. Over time, it packs extra minerals into that surface, making it super hard and sclerotic. That's great for the tooth, but it's terrible for us. Trying to bond to this is like trying to use Elmer's glue on polished granite. It's just not going to work. We have to chemically rough up that surface first.
And this is how we do it. We use a gentle surface conditioner. Now, people have tried a bunch of different things, but the science is crystal clear. A 10 to 15% solution of polyacrylic acid is the best tool for the job. It's gentle enough that it doesn't blast open the dentin tubules, but it's strong enough to clean off the smear layer and activate the surface for bonding. This is the key. Now, the protocol here is simple, but you have to follow it to the letter. Step 1. Put the conditioner on every surface you want to bond to. Step 2. Leave it alone for exactly 30 seconds. Step 3. Rinse it off completely with the water spray. And step 4, this connects back to our hydration balance, gently air dry it, but do not blast it dry. You want to get rid of any pooled water, but leave a moist, satin-like finish, not a frosty, bone-dry surface. All right, final pop quiz. To get that tooth surface ready for that critical chemical bond, which agent is our proven go-to choice? Is it A, B, C, or D? The answer, of course, is C, polyacrylic acid. So let's wrap this all up with your GIC clinical cheat sheet. Number 1, for strength, you always need to create a 0.75 millimeter butt joint margin. 2, master that hydration balance. Protect the GIC from getting too dry or too wet while it sets. 3, to get that bond, you have to condition with polyacrylic acid for 30 seconds. And 4, always think conservatively. Use techniques like the tunnel prep to save the tooth's natural strength. Following these rules really takes glass ionomer from being just another filling material to being a predictable, therapeutic, and really powerful tool in your hands. Which kind of leaves us with one last question. As these materials keep getting better, stronger, prettier, and easier to use, what new clinical problems do you think GICs will be able to solve next? The advanced clinical techniques that really separate a good restoration from a great one. You know, the stuff that can make or break your work. So, let's get into it. So, here's what we've got lined up. We'll start with the matrix challenge, basically how to keep that filling where it belongs. Then we'll get into a custom fix for those tricky spots near the gum line. After that, we'll talk about why you have to let these things mature, what that even means, and why finishing is a two-step dance. And of course, we'll wrap up with a little quiz to make sure it all stuck. All right, first things first, the matrix. Look, squirting the cement in is the easy part, right? The real trick is shaping it, getting that perfect contour so it just blends in with the tooth. And that, my friends, is where the real challenge kicks in, especially when you're working in those awkward, hard-to-see spots. So that really brings us to the big question. How in the world do you get that perfect shape every single time? Well, the secret is all in the matrix. And trust me, this is not a one-size-fits-all kind of deal. You've got to pick the right tool for the job. And this is a perfect example of what I mean. If you're working on the front teeth, it's pretty simple. You can usually just use a flexible little strip, kind of like you would for a composite. But the second you move to those cervical cavities, right at the gum line, things get complicated. Those pre-made cookie-cutter matrices, they just can't wrap around the complex curves of a root surface. No way. Okay, so if the standard stuff doesn't work for these areas, what do? We need a custom solution. Something that's made to order for that specific tooth. And here's our hero, the malleable aluminum cervical matrix. The magic word here is malleable. You can literally bend and shape this thing to create a perfect custom-fit matrix for that exact tooth. This is an absolute game changer, especially for those nightmare cavities that creep into the furcation areas of molars, right where the roots split. So what does the process look like? It's pretty cool, actually. First, you press and adapt the matrix right onto the tooth before you place the filling. You get that perfect shape, and then you just pop it off and set it aside. Then you do your thing. Condition the tooth, place the GIC with just a little extra. And then comes the crucial part. You carefully slide that custom matrix right back into place. That's what gives you the final shape. Okay, now lean in for this one, because this image shows the #1 mistake you have to avoid. Seriously. Look at diagram B. See how the matrix goes past the edge of the cavity? That's perfect. Now look at A. Yikes. See how it's caught inside the cavity on the bottom floor? That is a huge error, and it creates a really nasty problem. And this problem has a name. It's called a negative ledge. The best way to think about it is like an overhang, but in reverse. Instead of the filling sticking out, you've got a gap where the tooth sticks out past the filling. And what does that create? A perfect little home for plaque. It's a recipe for gum problems later on. It's one of those silent failures you really have to watch out for. So how do we stop that from happening? Here's a fantastic clinical pearl for you. Use a retraction cord. By just gently packing a cord, you move the gums out of the way. This gives you a crystal clear view and makes sure that matrix slides right into place, below the edge of the cavity where it's supposed to be. Okay, let's fast forward. Your matrix is perfect, the GIC is in, and it's got its initial set. You can take the matrix off, but hold on. The job is not done. Not even close. The cement is now entering this super vulnerable stage called the maturation phase, and it needs your protection. So why all the drama? What makes it so vulnerable? Well, you've got to remember that GICs are water-based. The whole setting reaction is this delicate dance with water. If it gets too wet, like from saliva, the good stuff can literally wash away. But if it gets too dry, it'll start to crack. It's like Goldilocks. It has to be just right. And this just right phase takes a while. I mean, you get that initial set pretty fast, so you can get the matrix out of there. But the real chemical hardening, that's still going on for at least an hour. And for some GICs, it's not truly done for a full 24 hours. Think about that. That's a whole day where that restoration is still, well, cooked. So how do we protect it during that time? Well, people have tried all sorts of things, from cocoa butter, yes, really, to different varnishes. But look, the science is pretty clear on this. The best, most effective thing you can use is an unfilled methylacrylate-based resin. Basically, it's a bonding agent. The light-cured ones are fantastic because you just paint it on, hit it with the light, and you're done, sealed and protected. And this whole long maturation thing brings us to a really important rule, and it's a big one. You cannot, I repeat, cannot, fully finish and polish a GIC in one appointment. It has to be a two-stage process, period. So let's break down those two stages. Stage 1 is early finishing. This happens right away, and your only job is to knock off any huge chunks of extra material. That's it. Stage 2 is final finishing, and that happens a day later, when the material is fully set. That's when you do the real work, refining the anatomy, polishing it up. And as you can see, the tools are different, and the precautions are definitely different. Okay, so let's walk through that first stage, the early finish. You're being super gentle here, just a hand instrument or maybe a very slow steel burr. Now here's the critical part. No water. Do not spray water on this thing. It will mess up the setting reaction. Instead, you're going to lubricate the burr with something like petroleum jelly. This keeps it cool. Then, the second you've trimmed the excess, you immediately paint on another layer of that protective resin. All right, now it's 24 hours later and it's time for the final finish. The GIC is nice and hard now, so you can break out all your usual finishing tools. Burrs, discs, strips, the whole shebang. But there's a catch. GICs still don't love heat as much as composites do, so you have to be gentle. And if for some reason you aren't using water spray, that same rule applies. Keep everything lubricated with petroleum jelly to avoid overheating it. Okay, we've talked matrices, maturation, and the two-step finishing process. You ready for a quick pop quiz to see what stuck? Let's do it. First step, what's the absolute best material to use to protect a brand new GIC restoration from getting too wet or too dry? Give you a second. Got it? It's that unfilled methyl grate-based resin. It's the best shield we have for that 24-hour setting window. Okay, question number 2. That negative ledge we talked about. That happens when the matrix gets stuck on the answer is the gingival floor of the cavity. Remember, it gets caught inside the prep when it should be outside, and that's what creates that nasty little trap. And for our last question, during that early finishing stage, what's the one thing you should never, ever use with your burr? Think back. That's right, water. You have to avoid water cooling. That setting cement is just too fragile, and the water will wreck the chemistry. Lubricate, don't irrigate. So let's just end with this idea. A great GIC restoration, it isn't just placed, right? It's a whole process. It's something that gets protected while it grows strong, and then it's perfected over time. It's about respecting the material's chemistry. A clinical casebook on a material that's in pretty much every dental practice, but can be, a little tricky to truly master. I'm talking about glass ionomer cement. We're going to go way beyond the instruction manual and tackle the real-world challenges and some pretty clever solutions that'll really elevate your GIC work. So this really is the big question, isn't it? We all know GICs are workhorses. I mean, they bond to dentine, they release fluoride, what's not to love? But we also know they can be notoriously fickle. You make one tiny slip up with moisture control, and that beautiful prep you just did can lead to a failed restoration. So this explainer is all about mastering that balancing act. So here's our roadmap. We're going to kick things off with the biggest hurdle, that moisture dilemma. Then we'll look at how GICs can be used for prevention as fissure sealants. After that, we'll unpack the brilliant sandwich technique and see its global impact with the ART method. And to wrap it all up, we'll run through a quick clinical checklist and quiz to make sure these key points really stick. Okay, case number 1. This is a scenario every single clinician knows all too well, the delicate dance of moisture control. I mean, if you get this wrong, even the most perfect, meticulous prep work is basically for nothing. This is the absolute foundation for success with GICs. And right away, we run into this central paradox. You see, GICs need a very specific environment to work. If you get that perfect bone-dry isolation with something like a rubber dam, you actually risk desiccating or totally drying out the tooth and the cement, which, believe it or not, weakens it. But on the flip side, if you let even a little bit of saliva contaminate the prep, the proteins in it form this slick film, a salivary pellicle, that completely blocks the chemical bond. It really is a clinical tightrope. So how do we find that sweet spot? It's all about finding the Goldilocks zone. A rubber dam, which is often our gold standard for isolation, can actually be too good here, leading to that cracked, over-dried surface. But then you have the other extreme, total contamination. The sweet spot is often right in the middle. Careful isolation with cotton rolls or dry guards is usually just right. It gives you enough moisture control without turning the tooth into a desert. But the key word, of course, is careful. But hey, what if contamination happens? You turn away for just a second and boom, the field is flooded. Don't panic, all is not lost. The key is to remove that salivary pellicle that has instantly formed. The protocol is simple, but it is absolutely crucial. You re-isolate the tooth, and then you treat the dentine with a polyacrylic acid conditioner for about 15 seconds. This little step essentially scrubs the surface clean and preps it for a proper chemical bond. All right, let's move on to our next case. Here, we're taking those same principles and applying them to prevention. We're not just restoring teeth anymore, we're using GICs as fissure sealants to stop caries before they even get a chance to start. Now, the initial challenge with this whole idea came down to simple physics, and it's captured by this one number, 100 micrometers. The pits and fissures on our back teeth are incredibly narrow, and the glass particles in the early GICs were just too big. They couldn't flow into any fissure that was narrower than 100 micrometers, so that meant they couldn't seal the very areas that were most at risk for decay. So you might be thinking, if resin sealants stick better mechanically, why would we even bother using GIC for sealants? Well, the answer lies in GIC's chemical superpower, its incredible caries inhibiting effect. The fluoride that it releases doesn't just sit there, it actively gets incorporated into the surrounding enamel, making it way more resistant to decay. And to solve that particle size problem, the pro tip is to use a GIC luting cement. They're designed with much smaller particles that can actually get into those tiny, narrow fissures. Okay, now for one of the most elegant and widely used applications of GIC. Case number 3 is the famous sandwich technique. It's just a perfect example of combining two different materials to get the best properties out of each one. The definition itself is beautifully simple. You're basically building a restoration in layers, just like a sandwich. The glass Ionomer cement goes down first, right onto the dentine, which it loves to bond to. Then, the composite resin is placed on top of that to act as the strong, wear-resistant enamel layer. This diagram shows the concept perfectly. You can see the GIC base providing that beautiful, bonded, fluoride-releasing seal right against the dentine at the deepest part of the filling. Then, the composite resin is layered over it, giving you the strength and aesthetics you need for the chewing surface. You really get the best of both worlds, the biological benefits of GIC with the physical toughness of composite. Now, this is a critical warning. The sandwich technique is not a repair job. It's not a cosmetic cover-up for a GIC filling that didn't turn out right. It absolutely must be planned from the very beginning of the procedure. And the reason for this is a huge diagnostic pitfall, which we're about to see. Right. If you don't plan the sandwich technique properly, you can walk straight into what's known as the radiographic trap. And this is a major diagnostic error that can lead to a perfectly good restoration being needlessly drilled out and replaced. So here's the problem. A lot of standard, older, restorative GICs are radiolucent. That means they appear dark on an X-ray, just like decay does. So if you place a radio-opaque composite over this radiolucent base, a future X-ray is going to show a dark shadow under your restoration that looks identical to recurrent caries. Another dentist, or heck, even you years later, could easily misdiagnose it and drill out a perfectly healthy restoration. The solution is really simple. Always use a purpose-designed, radio-opaque GIC-based material for your sandwich technique. For our final case, let's look at a technique that has had a truly massive global health impact. Case number 4 is the Atraumatic Restorative Technique, or ART. It leverages unique properties of GIC to deliver care in some of the most challenging environments you can possibly imagine. You should really think of ART as the field medicine of dentistry. It was specifically developed for use in parts of the world with limited or no access to electricity, to dental drills, or even to highly trained dentists. It's a way to manage cavities and restore function using a minimal kit and a very, very smart material. This table breaks down the core parts beautifully. Simple hand instruments, like chisels and excavators, are used to get into the cavity and remove as much of the decay as possible. No drills needed. Then, the cavity is filled using a specially modified high-strength GIC. Now, as you can see, aesthetics aren't the top priority here. The goal is to stop the disease and restore function. And it's a mission that ART has been incredibly successful at all around the world. Okay, we've covered a ton of ground, from the tiny details of moisture control all the way to global public health. So let's run through a quick clinical checklist to really lock in these key takeaways. Ready? First one up. Think back to that sandwich technique. What's the potential radiographic error, the trap, if you use a standard, older grade GIC for your base layer? Exactly. The radiolucent GIC shows up as a dark shadow on the X-ray, creating a false positive that looks just like recurrent decay. It's a perfect example of why selecting the right material from the start is so critical. Question 2. We know that resin sealants might stick a little better mechanically, but what is that unique primary advantage that GIC brings to the table when you use it as a sealant? Perfect. It's all about the chemistry. That sustained fluoride release actively makes the enamel more resistant to acid attack. It provides this powerful biochemical protection that goes way beyond just being a simple mechanical barrier. And for our final thought, glass ionomer cement has been a clinical workhorse for half a century now. So looking ahead, with its unique combination of adhesion, fluoride release, and biocompatibility, what new clinical challenges do you think this remarkable material is going to help us solve in the next 50 years?